All right, so you here? Could you, sorry, grab one of these handouts up at the front of the classroom? Because we're going to be using them today in a little bit. I want to show you guys something just real quick. The handout that you received today is your equation sheet for your next exam. So I have a digital copy of it already uploaded onto Canvas, both for today's class meeting. Here we go. So table of parallel and series RLC responses for today's class meeting, as well as for the exam two stuff. So you're going to be using this sheet extensively, effectively over the entirety of the next module. I have not yet uploaded the homeworks. I'm going to try to get that done today, and I'm just going to do what I did like the last section and just literally have all of the homeworks for this entire module up and opening up when you need them and all that kind of stuff. The due date for these homeworks is a little bit longer out than the due date for the homeworks for the op-amp section, largely because while I think you guys should be perfectly capable of starting the homework for parallel RLC circuits today. For whatever reason, sometimes it takes a little bit longer for this material to click, which is why I have dedicated a class meeting specifically to just working extra example problems to just make sure that everything makes sense. So your first homework set for this material isn't going to be due until after we have that day where we just literally do nothing but work example problems just to make sure everybody's on the same page. So you could start it now. I'm not telling you to procrastinate by any stretch of the imagination. But if you look at it and you're like, I don't know what the hell's going on, we have a day dedicated literally just to sorting that out. Okay. So let's go ahead and get cracking. So today we are going to cover the total response of parallel RLC circuits. Okay. Really what we're going to do is we are going to look at the natural response of an RLC or a parallel RLC circuit, and then use our expertise in analyzing RL and RC circuits from circuits one to figure out what's going to happen when we include a forcing function or just a voltage source or current source that's present at t is equal to infinity. Okay. So let's look at a simple circuit. So let's say that I have some current source IS connected in parallel with some resistance here. And because this resistance is literally not going to be important at all, I'm not even giving it a label whatsoever. That is intentional. Then over here on this side of things, we're going to have a resistance R in parallel with an inductance L in parallel with some capacitance C. Here I have a switch that is opening at t is equal to 0. And let's define a few things here. So this voltage that I'm identifying here, I'm going to call it V of t. We are going to treat this like it is a capacitor voltage because it literally is the voltage drop across our capacitor in this circuit. However, it is also the voltage drop across the inductor labeled L and the resistor labeled R, because all three of those elements are in parallel. Okay. I'm also going to define some currents here. So this will be my resistor current IR. Here's my inductor current IL. And here's my capacitor current IC of t. So let's talk our way through things here very briefly, okay? So at t is equal to 0 minus, our switch is closed, okay? So at t is equal to 0 minus, much like we had with our RL and RC circuits, that represents the time of DC steady state, okay? So at t is equal to 0 minus, and I'm going to put down here DC steady state, our circuit is going to look something like this. Actually, it's a mistake. Because we're at DC steady state, our inductor should look like a short circuit, and our capacitor should look like an open circuit. I'm going to go ahead and define things again really quickly here. So this is going to be IR at 0 minus. This will be IC at 0 minus. This will be IL at 0 minus. And this will be V at 0 minus. So what can we see from the jump here, right? So what is V at 0 minus going to be? So it's the drop across the resistor, sure, but it's also the drop across the inductor and the drop across the capacitor. At t is equal to 0 minus, since our inductor is behaving as if it were a short circuit, we're taking the voltage drop across the short circuit, which is always 0 volts. So V at 0 minus must be 0 volts. So this means that the energy stored by my capacitor at 0 minus is 0 joules, right? Because we know that the energy stored by a capacitor is 1/2 CV squared. If V is 0, the energy stored is 0. What is the current that's going to flow through our resistor in this case? 0 amps, okay? Sorry, the current that's going to flow through our inductor. All right. And because our inductor current is non-zero, we know that the energy stored at 0 minus for our inductor is greater than 0 joules. So we have some amount of stored energy in our inductor. And then lastly, the current flowing through our capacitor has to be 0 amps because no current can flow through an open circuit. So this circuit right here contains multiple energy storage elements, but because of its particular configuration, only the inductor is presently storing any energy, okay? So now let's look at what's happening. So for t greater than or equal to 0 plus, this is our transient condition. So we have our current source over here. our resistance that's value literally doesn't matter. This is our resistor R. This is our inductance L. Here's our capacitance C. And once again, I'm going to label things. So here's V of T, IR, IL, and IC. So when we had just an RL circuit or an RC circuit, we knew that effectively what was going on during the transient condition was that our energy storage element was just converting or giving its energy over to the resistor, which was converting that energy into heat, okay? And we knew, based on the differential equation that governed those relationships, that the current in our inductor or the voltage drop across our capacitor exponentially decayed at a particular rate that was related to the time constant, again, where the time constant was related to the values of the components in the circuit, okay? Well, we have something similar here, except that we have multiple energy storage elements. So we know that for this particular configuration, at t is equal to 0 minus, our inductor had some amount of stored energy. Well, now at t is equal to 0 plus and greater, our inductor can not only transfer energy to the resistor, but it might transfer some of it to the capacitor as well. And then over time, the capacitor will transfer its energy back to the inductor and to the resistor. And so we have this kind of confluence of energy being traded back and forth between our energy storage elements. Ultimately, the resistor will wind up converting all of that stored energy into heat over time. So what we're trying to figure out here is the mathematical relationship that explains exactly what the heck is going on, okay? And we're going to approach this very similarly to how we did it in circuits 1. We are going to come up with some type of differential equation and then make a guess as to what functional form satisfies that differential equation and go from there. So if I were to apply Kirchhoff's current law at the top right node, I would see that IR plus IL plus IC has to equal to 0. Kirchhoff's current law can never be violated because it's simply the law of conservation of charge as applied to circuits. Now, all three of these currents can be expressed in terms of that voltage V of T that is common to all of the elements, right? So for our resistor, that's just going to be 1 over R times V of T, just Ohm's law. For our inductor, that's going to be 1 over L times the integral from T naught to T of, V of T prime dt prime plus IL at T naught, so whatever initial condition we had, plus C times the derivative of the voltage with respect to time is equal to 0, right? So I'm just using the current voltage relationship, excuse me, that we learned in circuits one for a resistor, an inductor, and a capacitor here. And I have what's known as an integro differential equation. How many of you guys have had Math 245 yet? A couple of you. So an integro differential equation is, in my professional opinion, a pain in the ass to deal with. So we are going to get rid of the integro differential equation by just taking the derivative of both sides of this expression, okay? So when I take the derivative of both sides of this thing, I'm going to rearrange stuff here really quickly. So I'm going to put my highest order term first. So when I take the derivative of my capacitor expression, that's going to give me C times the second derivative of my voltage with respect to time. Now I'm going to take the derivative of the resistor term. So that's just going to give me a first derivative. Now I'm going to take the derivative of the integral term, which means it's just going to effectively cancel out, and we're going to have a factor of 1 over L times V of t. And now I'm going to take the derivative of my initial condition, which is a constant. So the derivative of that term is going to go to 0. And now, and the reasons for this will be more obvious actually in a couple of days. I'm going to divide both sides through by c so that the coefficient on my second derivative term is simply 1, okay? So I have the second derivative of the voltage with respect to time plus 1 over RC times the first derivative of the voltage with respect to time plus 1 over L times V of t, which I will often refer to as the 0th derivative of the voltage with respect to time is equal, excuse me, LC here is equal to 0. This equation right here is a second order homogeneous differential equation. Okay. So in order to solve this equation, or this differential equation, we need to figure out what form the voltage needs to take. So we're looking for a function where the first derivative and the second derivative and the function itself could combine together to make 0. So what kind of function satisfies that? So when we were looking at RL and RC circuits, we had a similar thing, but we had a first order linear homogeneous differential equation. So we were looking for a function when we were in circuits one, where the function and its derivative could combine together to make 0. So effectively, the function and its derivative need to be of the exact same form. What did we come up with then? An exponential. Is the second derivative an exponential? Does that look like the first derivative of an exponential? Yeah, it's also an exponential function. So we are just going to use the exact same exponential function as our guess here, okay? So we are going to guess that our capacitor voltage in this system will generically be of the form AE to the ST volts. So if we assume this for our capacitor voltage, let's go ahead and do the math explicitly here, okay? So the second derivative of AE to the ST is going to be S squared AE to the ST, right? So we are going to have s squared ac e to the st plus 1 over rc times the first derivative, which should be sa e to the st. Actually, there shouldn't be a c here. I knew that looked wrong. I already took care of that when I divided things out. So just s squared ae to the st. Sorry about that mistake. And then I'm going to have 1 over LC times AE to the ST is equal to 0. And now I'm just going to group things together. So I have a common factor of A in all of the terms. I can take out an S squared, a 1 over RC times S, and a 1 over LC, and I have a common factor of e to the st as well. This guy right here is the characteristic equation for this second order differential equation. Okay. So much like we saw in circuits 1, there are a couple of different ways that we can make this thing 0, so we're going to talk through what they are. The first way is that A is equal to 0, but if A was equal to 0, then that means that effectively we had no stored energy in the system to begin with, and so everything is just 0. So that's a solution, but it doesn't really represent our system, okay? E to the st will approach 0 if s is a negative number, but we don't really have any way to justify that assumption, right? So we need to make that characteristic equation equal to 0, much like we did in circuits 1. Now, in circuits 1, it was kind of easy because it was just a first order polynomial. Well, here we have a second order polynomial, commonly called a quadratic equation. So we're going to pull out our 8th grade math, and we are going to use literally the quadratic formula in order to figure out what values of s make this thing 0, right? So I'm going to put a little note up here. So this coefficient of 1 over RC is going to be the B in our quadratic equation. This factor of 1 over LC is going to be the C in our quadratic equation, and the A in our quadratic equation is just 1, right? So we know that we're going to have two solutions because this is a quadratic equation. So if I'm remembering correctly, we should have negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So let's substitute things in here. So the negative b is going to look like negative 1 over RC. Then we're going to have plus or minus the square root of b squared. So I'm just going to put 1 over RC quantity squared. So minus 4 times A, so A is just 1, times C, which is 1 over LC. All divided by 2. Now what I'm going to do is I'm going to move that 2 from the denominator up into the numerator, just so that I don't have fractions on top of fractions and all of that kind of stuff, because I don't really like it, okay? So that's going to look like negative 1 over twice RC plus or minus the square root of. So when I move that 2 inside of the square root sign, it's going to look like a factor of 1/4, right? Well, I'm going to distribute that 1/4 among things. So I'm going to have 1 over twice RC here. And I'm going to do something a little bit odd here. So the 4 and the 4 are going to cancel each other. The 4 and the 1/4 are going to cancel each other out. And so I'm going to put this as 1 over the square root of LC squared here. So these are what my two solutions are going to be. Now, in electrical engineering, these terms have special names, okay? So we are going to call alpha that factor of 1 over twice RC, okay? So alpha is what's known as the Neper frequency, measured in Nepers per second, where Neper is a dimensionless quantity, and it's effectively playing the role of something similar to a time constant in these second order circuits, okay? So it's describing how the exponential decay is going to occur. Omega naught, we are going to define as 1 over the square root of LC, where omega naught is what's known as the resonant frequency. Measured in radians per second, where a radian is also a dimensionless quantity. Okay. So the resonant frequency has multiple different meanings, even within the field of electrical engineering. One meaning of the resonant frequency is it's the frequency at which the impedance of the network appears purely real, meaning that all of the positive reactance contributed by the inductor is completely canceled out by all of the negative reactance contributed by the capacitor. That will absolutely be true here, but because we're not really looking at this system as a frequency dependent thing, that's not really what's going on in this case. It's true, but that's not really what we're looking at. So at the resonant frequency, this is a bad description, but it's really as good as I can think of. It's when our energy storage is doing its best. And so what I mean by that is like any small input gives us a large output variation. So we can convert any stored energy into a large voltage swing or current swing. And we'll see kind of how that manifests when we actually look at the responses of things here in a moment. So in terms of our Neper frequency and our resonant frequency, we can say then that S1 is equal to negative alpha plus the square root of alpha squared minus omega naught squared. And S2 is equal to negative alpha minus the square root of alpha squared minus omega naught squared. So we have a little bit of a problem in as much as our guess value of an exponential function has actually given us two possible solutions for S, the natural frequency, which will cause our characteristic equation to go to 0. So we are going to amend our guess value slightly. You can think about this as effectively just applying superposition. So instead of saying V of t is just A e to the st, we're now going to say that it's A1 e to the S1t plus A2 e to the S2t. So this might seem a little weird, but think about it in this context. So when we were dealing with first order circuits, so RL and RC circuits, what did the value of A, that coefficient out in front of the exponential, what was it related to? So I'm just going to do something here kind of as a quick review thing, right? So for a first order system, we found out that y of t was equal to y at 0 plus e to the negative t over tau for t greater than or equal to 0 plus. You guys remember that? Okay. So this guy right here is the coefficient A. Okay. So A was related to the initial condition on our circuit element of interest. Well, because in an RLC circuit, we have two energy storage elements, we have two initial conditions to keep track of, and they show up here as A1 and A2. Okay. So it might seem odd that we wind up getting a sum of exponential functions as the functional form of our voltage, but it has to be this way because we've got two initial conditions that are governing how the system is going to behave. All right, so let's take a couple of looks at things here. So we have this relationship. We're going to give it a special name here in a moment, but we are going to look at these guys, S1 and S2, a little bit more formally. Okay. So let's say that so for circuits, that should be where, not Weiss. Alpha is greater than omega naught, right? Won't always be true because we can make alpha greater than or less than or equal to omega naught depending on what elements we have in our system. But for circuits where alpha is greater than equal to omega naught, we're going to wind up having our voltage of the exact form that we just wrote down. A1 e to the S1t plus A2 e to the S2t. Okay. Now, a consequence of this is that S1 and S2 will be negative and real. We call this an overdamped system. So whenever alpha is greater than omega naught, we have an overdamped system, and our signals, right now we're explicitly saying it's just the voltage drop across all of our elements, but we know that it should relate to all of our currents as well, since all of our currents can be expressed in terms of this voltage drop. We'll follow this mathematical expression. Okay. for circuits where alpha is equal to omega naught. So if alpha is equal to omega naught, what's happening to S1 and S2? They're the same thing, right? So I'll put that down here. S1 will be equal to S2. What's that going to do to our expression that I've outlined here in blue? So if I had A1e to the negative alpha t plus A2e to the negative alpha t, I could just add those together. Well, that's a little bit problematic because that's just effectively giving me one initial condition to deal with, the combination of A1 and A2, okay? So for reasons which, I'm trying to think about how to put this. I'd love to say they're explained well in your Math 245 class, but I don't know that they are because I don't remember them explaining it. But effectively, whenever S1 is equal to S2, we have to modify our expression for our voltage, in this case, slightly, in order to take into the account that we need to have two distinct initial conditions that are governing things. Okay. So we're going to make that happen by using this expression. So we're going to have A1 T e to the negative alpha t, sorry, plus A2 e to the negative alpha t. And so that extra factor of time there on the first term is enough to kind of break this up and make both initial conditions important. At some point, I will find the time to actually look into what that really represents, but this is the standard practice for a second order differential equation where what are called our eigenvalues, the values of S1 and S2 are the same. Okay. So we call this critical damping, or a critically damped system, okay? And here in a moment or two, I will draw out what each of these responses might look like so we can kind of see the difference between the types of dampening that we're experiencing. Okay. So in our last case, we'll have alpha less than omega naught. So let's come back up here and let's look at S1 and S2 and see what happens when alpha is less than omega naught. So anybody have any thoughts? So what's happening with the stuff under the square root sign? Right. So alpha squared minus omega naught squared will be a negative number. And because we have the square root of a negative number, we have an imaginary number. 100% correct, Sebastian. So now that imaginary part for S1 and S2 are going to be identical. Because alpha, we have alpha squared minus omega naught squared under a square root sign for both S1 and S2. So we have negative alpha plus some imaginary number, and then negative alpha minus that exact same imaginary number. What do we call that? They're complex conjugates. You guys remember what a complex conjugate is? So we can say that S1 is the complex conjugate of S2 or vice versa. Okay. Now, our original expression using Euler's identity could actually be rewritten as V of t is equal to B1 cosine omega dt plus B2 sine omega dt times e to the negative alpha t, where omega d is defined to be the square root of omega naught squared minus alpha squared. Okay, that's literally nothing more than our original equation. For whatever reason, all of the textbooks seem to use coefficients B1 and B2 instead of A1 and A2 for our initial condition terms here. And this comes from the fact that we know that e to the j omega t can be written as cosine omega t plus j sine omega t. Just coming from Euler's identity and then doing a little bit of complex number manipulation, right? So this type of system is what's called an underdamped system. Okay. So now I'm going to make a plot. And this is, to some extent, a bit of an exaggeration, but it'll be okay. And I'll explain even what I mean by a bit of an exaggeration here. So I'm going to start with a critically damped response, okay? So I'm going to start at some value. And we are going to see that our system effectively just looks like it exponentially decays, something like that. So our red curve is for critical damping, and it takes some amount of time for it to effectively, for our voltage drop across our capacitor to effectively fully discharge. Okay. For an overdamped system, which I'm going to do in blue, we're going to have something similar. But it takes longer for the system to settle to its final value. Okay. So that's the difference between over damping and critical damping. So realistically, actually, we would talk about this in the opposite form. So an overdamped system takes a long time for it to decay down to its final value. A critically damped system decays to its final value as quickly as it can without overshooting the final value. And what I mean by that will be obvious when we look at an underdamped system. Okay. So in an underdamped system, we'll hit the final value very quickly, but we're actually going to shoot on past it. And we're going to ring exponentially like so, so that the envelope of this curve looks like an overdamped curve. So when you're working example problems and all of that kind of stuff or homework problems, I'm going to ask you to simulate circuits. When you're looking at an underdamped system, you should expect to see some ringing, but it depends on how close, or excuse me, how much, what the difference between alpha and omega naught is. So if they are very close to each other numerically, then it's going to look a lot like a critically damped system. Whereas if omega naught is much, much greater than alpha, you're going to see lots and lots of ringing. Similarly, looking at our overdamped system, if S1 and S2 are very close to each other numerically, it's going to look a lot like a critically damped system. But if S2 is much more negative than S1, it's going to take a very long time for it to settle. Okay, so they're all related to each other, and it's all related to how long it takes things to settle to a final value. Okay. So now I want you guys to look at your table of parallel and series RLC circuits, and I'm going to open this up so that there will be a recording of it as well. So I have organized this table for you guys so that we can see very easily what alpha is, what omega naught is, depending on if we have a parallel circuit or a series circuit. And then I've also organized it so that we can see what our responses are going to look like for an overdamped system, a critically damped system, and an underdamped system, okay? Now, I've provided several pieces of information here, and you'll kind of see why in a couple of moments. But the thing that I want to draw your attention to is the fact that when we just looked at everything, we didn't have this y at infinity bit here, right? So that y at infinity bit is effectively what's going to happen when we look at the total response. So we just need to add into our response equations that are forcing functions, so our voltage sources, current sources, et cetera, that are still connected to the circuit at t is equal to infinity are going to have some impact. Instead of having that weird difference relationship that we saw in our first order circuits, it's literally just add it to the natural response. Nothing remotely hard or anything about that. Okay. So I have this expressed as y of t as opposed to v of t or anything like that, explicitly because all of our voltages and currents in a RLC circuit are going to behave the same way. So if one of those signals has that type of response, all of them have to have that exact same type of response because of Kirchhoff's current law and Kirchhoff's voltage law. So we can apply the relationships that we just went through generically to literally any circuit element. It's always going to work. So here I have the response, and then underneath, I put the derivative of the response, okay? So we're going to talk in just a moment about why the derivative of the response is so important by looking at a circuit, okay? And I'm going to talk you guys through the process that we are going to use for solving these things. So let's look at this circuit. Okay, so I just got a random one of my 8 different circuits textbooks. And we're just going to work an example. So here I have a 9 milliamp source. Six kilo ohm resistor. Here's a switch that is closing at t is equal to 0. Here's a 62.5 Henry inductor. Just using the values in this textbook, that seems like an excessively large inductor to me, but it is what it is. A 2.5 microfarad capacitor. Three kilo ohm resistor, and a 15-volt source over here. All right, so let's say that I want to solve for a couple of different quantities, and we only have 20 minutes left. Let's make them fairly straightforward. I want to solve for this inductor current, IL of t, and I want to solve for this resistor voltage, VR of t. Realistically, these are the only two things that we're going to need to keep track of here. So let me say that by stating the resistor voltage is going to be the exact same thing as the capacitor voltage. Okay. So if I were to put the capacitor voltage over here, in purple, during the transient condition, with our switch closed, the 6 kilo ohm resistor is in parallel with the 62.5 Henry inductor, is in parallel with the 2.5 microfarad capacitor. So the resistor voltage and the capacitor voltage are literally the exact same thing. Okay. So we actually have two different options here to solve for things, okay? So we can solve for the capacitor voltage first and use that to determine our everything else. Or we could solve for the inductor current first and then effectively just use the relationship that since the inductor voltage is the same thing as the capacitor voltage, once we know all of the coefficients for the inductor, we are done. So that's the route that I'm going to take here. I'm always going to try to choose the most efficient route, even though there are usually 5 or 6 different ways that we could get the result I'm looking for. Okay. So in order to solve this thing, we're going to start by analyzing our circuit at t is equal to 0 minus. Okay. So at t is equal to 0 minus, we've got 9 milliamps. Six kilo ohms. Our switch is open. Here is our inductor as a short circuit. Here is our capacitor as an open circuit. Here's our 3 kilo ohm resistor. There's our 15-volt source. Let me just define some things that we're going to need to keep track of. So, oops, let's turn that to blue. So here's VR of 0 minus, IL of 0 minus, and VC of 0 minus. So Somebody hit me with what you think some of these quantities are going to be. So let's start with one that I think is real easy. What's VC of 0 minus going to be? I disagree. Disagree. 0, because the capacitor is in parallel with the inductor, and the inductor looks like a short circuit. Yeah, VC is 0 volts. Now let's do VR. 54, right? 9 times 6 is 54. What's IL at 0 minus going to be? I think it'll be negative 5 milliamps because of the polarity of the voltage source. So just to be clear, that's negative 15 volts over 3 kilo ohms. Direct application of Ohm's law, nothing too wild or crazy there. All right, so we all okay with this analysis at t is equal to 0 minus. Okay. Step 2 will be to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is closed. So here's our 9 milliamp source. Our 6 kilo ohm resistor. Here's our inductor. We're going to do the exact same thing that we did in circuits 1. We're going to replace our inductor with a current source at t is equal to 0 plus. So we know that our inductor current is supposed to be negative 5 milliamps direction down. So I'm just going to put that here, negative 5 milliamps. It wouldn't, so we could call that 5 milliamps up, and then just for shits and gigs here, I'm going to call this IL at 0 plus. So the voltage drop across our capacitor at t is equal to 0 minus was 0 volts. So that means our capacitor is going to look like a short circuit at t is equal to 0 plus. There's our 3 kilo ohm resistor. Here's our 15 volt source. So we have this voltage VR at 0 plus, and this voltage VC at 0 plus. So let's run through some things really quickly. We know that the voltage drop across a capacitor cannot change abruptly. So whatever VC at 0 plus is has to be what VC at 0 minus was, which is 0 volts. Same thing for IL. So the current flowing through the inductor at t is equal to 0 plus has to be the same as the current flowing through the inductor at t is equal to 0 minus. So that's going to be negative 5 milliamp. The other thing that we might need to be keeping track of is VR at 0 plus. What's that going to be? 0, because it's in parallel with the short circuit. Absolutely. Now we're going to analyze things at t is equal to infinity. So at t is equal to infinity, we are once again at DC steady state. So our inductor should look like a short and our capacitor should look like an open circuit. Our switch, however, will be closed. My apologies. So here's my inductor. Here's my capacitor. Label things. So let's start with the easy stuff first. What's VC at infinity? Still 0 volts. What's VR at infinity? 0 volts. So IL is where things are going to get a little bit more difficult. Anybody have any thoughts on this guy? Yep. So we have 9 milliamps flowing in this way from our source. And then we have -5 milliamps flowing in this way from our voltage source, right? So adding those guys together, I think, is going to give us 4 milliamps. So now we need to, so this is step 4. Determine if the circuit is overdamped, critically damped, or underdamped. We're going to do this by simply calculating alpha and omega naught. Okay. So omega naught is only dependent on the inductor value and the capacitor value. So that bit is rather easy, right? So omega naught should be the square root of 1 over LC. So that is going to be the square root of 1 over 62.5 henries times 2.5 microfarads. Let me grab a calculator really quickly. $80 radians per second. To determine alpha, it's going to be a little bit more difficult, okay? And the reason why I say that is because there are multiple resistors in this circuit. So we are going to do effectively the exact same thing that we did to calculate the equivalent resistance of our circuits when we were looking at transient analysis in circuits 1. Except this time, we're going to remove both energy storage elements and look in through their terminals, which should always be fairly straightforward for us because we have either a parallel combination or a series combination. We'll get to there in a minute. Okay. So during the transient condition, my circuit looks like this, right? So 9 milliamp, 6 kilo ohm. Here's my inductance. Here's my capacitance. Here's my 3 kilo ohm resistor. Here's my voltage source. So we're looking for the equivalent resistance of this thing, which means we need to be looking at a dead network, Okay, so all we're doing is finding the Thevenin equivalent resistance with respect to our energy storage element. So let's start by looking at a dead network. So how do I turn off my 9 milliamp current source? Open circuit. How do I turn off my 15-volt source? Short circuit. Now I'm going to remove my energy storage elements. And so what do I see? To me, it looks like 6 in parallel with 3, right? Oops. 6 kiloohms in parallel with 3 kiloohms. So 18/9 is 2 kiloohms. So from this, alpha is 1 over twice REQ times C. So that's 1 over 2 times 2 kiloohms times 2.5 microfarads. Comes out to be 100 nepers per second. So since alpha is greater than omega naught, we know that this circuit is overdamped. All right, I'm going to save these notes and we're going to finish this problem up at the beginning of class on Monday because I ran out of time. So we did it over the inductor and the capacitor because they're in parallel. So I took them both out and I just gave them a single set of terminals, right? Is that okay? Just making sure because that's one of the weird things. We got to take both of them out at the same time and look into the terminals that were left behind. Yeah. All right. You guys have a good weekend. Like I said, I will put the homeworks and all that kind of stuff up. That being said, we didn't even finish a single example problem, so I definitely don't expect you guys to start working on stuff just yet. You could do the first 4 steps of each problem because that's what we did here. But you won't be able to do the last couple of steps. So anyway. All right. Have a good weekend. See you on Monday.